Hello all, welcome to our final event for the undergraduate maths colloquium of this academic year. I started the first talk and I will be doing the final one. And today I'll be talking about Monte Carlo and some statistical method involving how to integrate. So essentially they're commonly known as Monte Carlo methods. And as among them, I'll be focusing on the Mcmc, the Markov Chain Monte Carlo. All the other possible Monte Carlo methods. And you are third year. Are you third year or second year? Okay. So I'll assume, okay, any of you know probability? No. The UTL one, yeah. How about you guys?
Yeah.
Law of large numbers.
Oh,
Central
yeah.
Limit Theorem.
Yeah.
Okay, so I'll start. Right. Section 1. Monte Carlo one. So in life, we integrate stuff. We do a lot of calculus and we try to integrate some functions. And well, some functions are easy to integrate. For example, right now, some functions are easy to integrate. For example, well, this we all know is just this. And for example, e to the x is e to the x. But these are pretty easy. And we have a quite elaborate literature on how to do these integrals. But sometimes when we try to do integrations in real life, it's kind of complicated because we'll come across integrals that are a bit hard to integrate. For example, an integral like this. What's the antiderivative of this? John, can you find an antiderivative of this? No. Yeah. Well, because it's hard. So essentially, it's such integral does not have a well enough antiderivative. So we call this intractable functions or integral. So essentially, if an integral does not have an antiderivative that is an elementary function, then we say it's intractable. So elementary essentially means it's of the form of a sum or product or composition of finitely many polynomials, rational, trigonometrical, hyperbolic, or exponential functions. So for example, technically this one is it's not intractable because cosine is trigonometric and exponential and x squared. But still, it's very hard to find a precise antiderivative. Now, how should we do it? How should we integrate? Well, if any of you took the easiest class in probability theory, you may realize that this is the probability density function of normal 0, 1. It's this. And we notice that, well, if you write out the full PDF of this normal mu sigma squared, it will be square root of 2 pi and then sigma something. And then minus x minus mu squared over 2 sigma. Correct me if I'm wrong, but it's something like that. So we have this. Now we have exactly this as well, and we're going to find x. So if you recall, expectation of x for continuous then variable x will be integrated around b following this PDF. So it's just integrate x, alpha x, x. Now this expression is actually similar to what we have here. So essentially, if we choose to compute the expectation of x, we'll get the sine of x, f of x, and dx. Now the f of x, we just assume that x follows this normal 0, 1. So the f of x, the PDF of it. So this f is PDF and this f is CDF. So this is the probability density function and the cumulative density function. Now this becomes the sine of x. The f of x, we substitute that. It will be e minus x squared over 2 dx. Now just take out this constant, not important. We can always put it back later on. Okay. So if you want to compute the value of this integral, you just need to compute expectation of cosine of x, where x is a random variable for normal 0, 1. Of course, it's a constant term that we just plug in later on. So now the question is, if you want to find this, we just need to find this. How do we find this? How do we find the expectation of this random variable? Or this function of random variable? Any ideas? So we can, any ideas? No?
So an example,
It's a random variable.
closed form solution.
By what? By using this. How do you close form this?
So
Well, of course, yeah, if you want to find a closed form expression of this, you're essentially finding this integral, which is exactly the question, so it's tautological. Yeah, what do you think?
so numeric.
No, behind you. But thanks.
You want to generate like a bunch of numbers of x.
Yes, you take samples from this. You take samples from x, and then you take the sine of it, and then take the average, because that's the expectation. Precisely, that's the Monte Carlo method. So the idea is that we generate samples following this normal 0, 1 distribution. Then these are our samples, and we'll just take the average of it. This will be expectation of x. What will be an estimate of this expectation of x? Because normally in the frequentist statistics, of course, most of you won't understand what I'm trying to say. But essentially, if you take the average of it, it will be a good estimate of this expectation of x, that particular fixed value. So you just take the expectation. No, the average. So this is just goes from 1 to n.
So we're approximating it.
Yes, it's an approximation. Yeah, so this is for expansion of x. So if we take the sine of x and then we take the bar of it, this is just x r. Now this is just approximately the sine of x, which is what we wanted. How is this approximation true? Well, this is the law of large numbers. So the law of large number states, well, essentially exactly that. So it's called a strong. It's still called strong law of large numbers. It states that well, if you have a pitch of m, bar defined to be m over 1, I to 1 and pitch of x, I. So essentially, it's just an average of the samples, and after function applied to it. But this thing converges almost surely to the expectation of this pitch of x. Now, what does it mean to converge almost surely? So if you know magic theory, this is known as almost everywhere convergence. So essentially, here is in the probability setting. So we're working in a probability space. So this, well, it's kind of like a percentage details, but if you know anything about magic theory and probability theory, this is the sample space. This is the sample space, this is the event. And this is the probability measure that we define on this. So this is like a probability measure. So it satisfies all the normal conditions for measure. In addition, that we have this. So if you measure this, the entire set will go to 1. So this almost surely convergence essentially means that the probability of the limit as n goes to infinity, or this is n here, of h of n r goes to the expectation of h of x. So this converges to this is probability 1. So if you talk about like almost everywhere, so it's kind of the same. We just measure the complement of the event and delta 0. Good. Yes. Any questions? John?
No.
Okay. Yeah, so that's the strong law of large numbers. So essentially, by strong law of large numbers, we can just say that, well, we can justify this approach. Of course, there's another piece of information that we want to think about. It's not going to contribute too much in this talk, but it's good to think about. This really focus on the biasness of this estimation. But how about the variance? So we know that this converges to this value, but that's only like it shows that it's unbiased or in statistical terms it's consistent. But how? Well, there are two questions really. So how fast does it converge? So that's the rate of convergence. And two, how well does it converge? So it's like, let me give you an example. If you have, let's just try here. But this kind of converges to some value here, right? But at the same time, these ones like kind of have an average of the same value, but it's a larger variance than the blue ones, black ones and the blue ones. So, well, technically, in both cases, we'll say that it converges to this value, like it's consistent. But obviously, the blue one is much better than the black one, as the variance is quite small. So that has to deal with the variance of the estimator, which is an interesting thing to talk about. Of course, if you have the bias, we have the biases, we have the variance, we construct a confidence interval to better bound our estimations. Now, a more systematic and more elaborate study of such methods, well, they're under the non-parametric statistics, which now we're going to talk about. So let's just erase this. Anyway, we know that this is a valid approach due to the strong law of large numbers, and yeah, let's see how it works. Ah, nice. So some live code. Can you guys see this? Yes, okay. So our idea is that if you want to compute this integral, we just generate samples from normal 0, 1. So this is R studio. Using the R language, you can use your favorite language like Python or something. It'll be the same. So here I generate multiple numbers. And then down here you can see that I've already done that. So basically I generate 100 samples from the normal 0, 1 distribution, and I'll run them off to 2 decimal points. Just make it look nice. So here. Oh yeah, for the Zoom, I will share the screen. However, then I'll go back and do the shit. Okay. Yeah, so essentially, I get 100 samples from the number 0, 1, and I run it off to dp, and shown here. Now to kind of see if this is in fact valid, let's just do a box plot or like a histogram of this. So we can see that it's roughly following the normal distribution that we kind of all know, but it's kind of like a bell curve. It's more or less there. And then the mean is around 0. Obviously, it's only 100 samples, so it's not that great. We increase the number by, let's say, it looks more faster. The hundreds. Look, this time it's much better as well. This is a random sample. So every time it changes. Now, if you want to fix it, we can use the set C function. That's no problem there. So next we do a cosine of it. So we just cosine all these samples, and then like this, and then we just sum them up. Well, not necessarily take a mean of it. It's 0.59. So that's this is power 0.59. And then we involve this root of 2 pi term. So just it'll be around 1.51. So if any of you guys want to pull out your famous or your favorite integral calculator and try to integrate this, you should get around like 1.51.
On which bound?
Which bound would mean?
The bound to integration.
Oh, so like
Negative variable.
yeah, this.
Because it's all going to be just that. Because
Yeah, I mean you could of course like do a bound just input this indicator function. Yeah. But here now we're just doing the entire thing. So it should be a relatively more accurate value. Now obviously to make it more accurate, we just increase the number of samples we have. Oh, it's going to take a while. I'll put too much 0 there. It's not. Yeah, so call it 1.52, going again, 1.52, 1.52. That's roughly 1.52. It's like a good idea of what value it should be. Right. Oh, shit. Okay. Now this is Monte Carlo method, or we normally refer to like this kind of method as the classical Monte Carlo or exact Monte Carlo. So obviously there are other ways for us to do similar stuff because when the problem gets even more complicated, we need a more complicated some sort of algorithms. So if this becomes extremely nasty, then obviously we can use more complicated tools. But just to illustrate the point of like Monte Carlo, this is the idea we go. And now, if you recall, here we kind of assume that like some part of this integral involves like a PDF of some random variable. So what if it doesn't? So what if it just x then plus 10 and square, and then we have a square of here. Those kind of random stuff. How do we do it? Well, it's not too hard. Integral of f of dx for some random f is just f over g dx. And then this g can be just a PDF of some random variable. So we can do exactly the same. So we sample from G, so some like some x from G, and then we just do the average of f over g of x, and we take the form. So we do the average. Now the question kind of is, how do we choose a good enough g such that this is going to be like accurate and like efficient? Well, there's a lot of guess and trials going on for these ones, but essentially it's doable. Or like integrating like an arbitrary integral using Monte Carlo methods. Obviously, you want to make this like around 1, so it's kind of accurate. Yeah. Right. So at this point, we have noticed that Monte Carlo method is actually quite helpful. So this is what I mean by integration using statistics. Essentially, it's this, the Monte Carlo method. But the whole Monte Carlo method builds on the assumption that we do indeed get samples from this distribution. Right? If you can get samples from distribution, then obviously you can do Monte Carlo, but if you don't, how are you supposed to do Monte Carlo? So the question becomes, how do we get samples from any particular distribution? Right? How do we get samples from any possible distributions or from some distribution? Well, that will be our second section. The Monte Carlo, the Markov chain Monte Carlo. And erase some stuff there. So MCMC stands for Markov Chain Monte Carlo. So essentially, it's a Monte Carlo method using Markov chain. So how many of you know Markov chain? Yeah, I mean, if you have listened for like any of my previous talk, or like you'll notice that I kind of talk about it a lot. But just for those who don't know, I'll do a very quick introduction to Markov chain. It will involve doing few examples, and I will just do some calculations and we'll learn. Okay, so this is like a example of the diagram for a particular Markov chain. So you can see that there are like 3 nodes here, or 3 vertices, 1, 2, and 3, and then there are a bunch of edges with directions. For example, this 1 goes to 2, 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 7. And then there are numbers on the edges. And then you can notice that all the outward edges with the values on them sum up to 1. So for example, like this is half plus half, 1/3 plus 2/3, and this is 1. So they all add up to 1. So essentially, this 1, 2, and 3. So like values here, 1, 2, 3. They're known as the state space. So it's just the collection of possible states. And the edges represent like the direction, and the values of them is the probability that it goes from this state to the other state. So essentially, you the probability that go to 1 condition on at 3, this would be like 1/3. So like notice that we are at 3 here, and it would probably for us go to 1, so that's 1/3. Now if it's like 2, it will be 2/3. Because we can just read it out on the graph. Now these values are known as the transition probability. Or more specifically, the 1 step. Because essentially we're going there in 1 step. The 1 step transition probability. Now we can combine all these transition probability into a matrix form. Because why not? So we have a state space of coordinate 3. So we just have a 3 by 3 matrix. Okay, so 1, 2, 3, 1, 2, 3. So we define it in this way. So Pij. So we call this matrix P. So this is a capital P, and do not confuse this with this. So this is the probability measure, just like probability, and this is just a name for this transition matrix. So Pij, so the Ij is an entry of this matrix, is defined to be the probability of at I go j. So P11 will be half, P12 will be half, P13 0, 21 will be 0, 22 0 and 1, 31 1/3, 2 0. Okay, let's erase this. Now notice that each row sum up to 1. Because it's a distribution. So a distribution kind of like has a property that sums up to 1. It's called the normality of the distribution. It's a name. So okay, this is good. We can kind of compress all the important information about transition in this matrix. So obviously call this the transition matrix P. Transition matrix. Now I say that it's a one-step transition probability. So what about two-step? So what exactly does it mean to do something like a two-step transition? Well, it means that probability of, let's say, go to I in 2 steps. Condition of at, let's say 3, and this is go to 1. So it means that probability of at 3 and then go k times the probability of go 1 at k. Yeah. So essentially, if we want to go from 3 to 1 in 2 steps, we go to some intermediate step first and go to 3. Then go to 1. So 3 intermediate 1. Now we don't really care what the intermediate step is, right? So we can sum up all the possible k here. Obviously, k must be an element of the state space. So in this case, it'll be like, I'll call this P31. So P31 is just like P3k, PK1, sum up of all the possible k. Well, if you recall anything from the linear algebra, 3k is kind of like this. And then k1 is kind of like this. So it's like this row and this column. And then we kind of do like the dot product of these two, like this row and this column. So it's kind of like so it's like 6. Yeah, these are all. And then we call this so this like which one?
No, he asked the question.
Oh, okay, yeah, that's fine. Yeah. So this superscript bracket 2 means that it's like 2 steps. Well, you can see from this that it's kind of like row times column. So we can generalize this by just squaring this matrix, right? So then you'll give us the 2-step transition probability. So we're just doing this for all the possible combination of 2 steps. And oh yeah, just to give some names. So equations like this is known as the Chapman-Kolmogorov equation. And then this is the 2-step transition matrix. Now we can just generalize this. Instead of 2, for n. So just keep like multiplying like p times p times p times p for n times, and we just get the n-step probability matrix. Question. Oh, this was not. As n goes to infinity, right? We just keep going. We're still going to like sort of reach this stationary distribution, like stationary kind of state, or is it going to, I don't know, going back and forth between two states or whatever, you know? What's the limiting behavior of the PM, or what's the long-run behavior of this major Markov chain? Let's do another example. Okay. So what's this entry? Can someone tell me what's the entry for this?
Oh, 0.7.
Yeah, this one?
0.8.
What is 0.8? Let us assume that this matrix is diagonalizable. And why it is, because these two are independent. So we can write P in the form of Q inverse Q for this is a diagonal matrix. This is some irregular matrix. Now Pn of this will just be this of n, and this is like, or if you do Q inverse, these two cancel out becomes identity, so Q inverse, and then Q. Now this is diagonal matrix, so if you do this, we just square it. And then by the property of a diagonal matrix, so basically this the elements here and this there are only possible non-zero elements or entries on diagonal, and the rest zero. So if you do the nth power, essentially we just put it nth power into any entries of the diagonal. So it's pretty easy stuff to do. So this is the square, so obviously you can generalize this to n. It will be this. It's an easy proof by induction. So essentially, if you want to do limits as n goes to infinity, essentially we just need to study this. Because these two are independent of n in this expression. So we just study this, and then for study this, we just need to study how well does this entries behave as n goes to infinity. Now this is pretty standard. Why? Because if this is because all of these are like no bigger than 1. So if it is 1, then it will go to 1. If it's not 1, it goes to 0 as n goes to infinity. So if you just study this, it'll be quite easy to do. So if you compute this, which I'm just too tired to compute at this moment of time, we'll get some fixed values. Let's just assume it's 7 over 15, 8 over 15, 7 over 15, 8 over 15. This is just an arbitrary value that is come up with. It may not be correct, or it shouldn't be correct, but let's just deal with that. So essentially, assume this is the actual long-run distribution or long-run transition probability. What this is trying to say is that for like 7 out of 15% of the time, the 7 out of 15 of the time, we're going to be inside state 1, and then for the rest, we're going to be in state 2. So now if you look at this row here, this is like 7 over 15 and 8 over 15. This 1 is 2. So this is a distribution. So it kind of tells us the long-run distribution of this chain. And what is a distribution with 2 possible values? So it's like a discrete case. Now here's the catch. Just now we have like 2 values, right? 1 and 2, like 7 over 15, 8 over 15. This is a distribution. But we also know that our normal 0, 1 is also a distribution. Obviously, it takes values from like the real line. but it is a distribution, and then for each point we kind of assign a value to it. Or like a Poisson lambda is also a distribution. So all the distribution we have are like a distribution. So what if we somehow find a way to create a Markov chain such that a lot of distribution of that Markov chain follows some particular distribution of our I don't know, some particular distribution we want. Is it possible? If it's possible, then it's quite good, right? Because the Markov chain can go on forever. And then when it goes on, we can just stop at some point, and after it goes on, after you reach the equilibrium distribution, then we just keep going under the equilibrium distribution. And if you just keep going the equilibrium distribution, then all the values, all the samples, and all the states you get will be samples following this distribution of like this target distribution. So it means that we can create like an infinite number of samples following some particular distribution if we can find a way to construct a Markov chain that kind of have an equilibrium distribution following the target distribution of our target distribution. And now that's the general idea of Markov chain Monte Carlo. Okay. Any questions so far? No? You get the point, right? Section 3, random walk metropolis, metropolis adjuster Langevin algorithm, Hamiltonian Monte Carlo. So these are like the acronyms of 3 possible algorithms for Mcmc. Now this is like the most basic one. This is like a more advanced. This is like the state of the art for like a while. I mean, no, it's still state of the art. So these are all like algorithms of Mcmc algorithms. I'll tell you what these algorithms are. So let me just write out this pseudocode. That's 0, 1, 2. Okay. Now this is the random walk. Metropolis. So essentially, let me just go through what this is trying to do. So we just repeat these steps for like n+1 times n. So we were given was x0, which is the starting point. And then we have a target distribution part. Targets. So for example, if you want to sample from a normal distribution, pi will be a normal PDF. If it's Poisson, then just follow from the Poisson PDF, exponential. So this is our target. And we will have this tuning factor, this sigma tuning factor. So it's like this. This like sigma is like sort of a parameter of our choice. And obviously, you see this is alpha, so this is called thing called proposal or rejection. Oh, acceptance. Yeah, acceptance rate or like acceptance function. We kind of have these inputs. So start from time 0. So we will sample of y from this normal x0 sigma squared. So this is just saying that y equals to x, not plus 0, 0 sigma squared. So this is like the starting point, and then this is sort of a noise. Basically, it's just a value from a normal distribution. Now, this I is because we can do this for like, like any arbitrary dimension. So if it's just like one dimension, we just don't need I. But if it's like two dimension, so that of dimension 2, then we just put I here, where I is like 2 by 2 identity matrix. So this becomes a multi-dimensional Gaussian random variable, like normal random variable. So we just do something like small perturbation to this x star, and then we get this new y. Right. Obviously, this sequence of this is something we can tune. We can adjust based on like we can just make some slight changes to the algorithm. Now, 2, we just sample from another value from uniform 0, 1. So it looks like uniform 0, 1 essentially is this 1, 0. Probability 1. Yeah. So 1. I think so. Yeah. Yeah. Essentially, we just like have an equal chance of getting any particular values between 0 and 1. Let's say like yeah. So we sample another what's called y from this uniform distribution, and we just say that if this u is smaller than this alpha xi y, where alpha is trying to be this, then we will accept this change. So we set a new, like the next step to be this new proposed y. If that's not the case, we will just not change it, and we just keep with this. So we just stay. This is like accept, and this is like reject. And then we just keep doing this for like n steps, and then we just get collection of x n. Now, ideally, this has an equilibrium pi. Now this acceptance function is this minimum of these two. So it's either 1 or it's this ratio of this pi of y of pi of x. This pi being the target distribution. Any questions so far? Okay. So now this is the random walk metropolis. So why do we call it a random walk? It's because this. But this is kind of like random walk, right? So like we start off at some x naught, and then we just do our like random walk, go up a bit, go down a bit. So it's like a random walk. So and the metropolis part something from this idea is that we don't accept any particular like a proposal, like call it a proposal. So we don't accept any proposal, we just accept like proposal that like somehow like good enough. And then how do we consider it's like it being good enough is by this acceptance function. Why is this? Oh, obviously this is not the unique choice. You can choose other acceptance function. But why do we view this? Well, it's actually kind of proven. Paper by Pashkun in 1970 something. So we just say that this is the optimal. So it's like Pashkun in his paper, he kind of like compare like two possible like basically like two most famous proposal like this acceptance function, and then he kind of proved that while all else equal, this is better. Now this is proposed by Metropolis, as you can tell from the name, and the other function that he's like considering was this called a Barker proposal. And then this is my metropolis. So Patch can prove that this is more optimal than this. Fun fact, metropolis is the advisor of Patch. So obviously, it's only published if this is true, right? Well, I think it's still a rigorous paper. So, well, anyway, this is not actually the precise or the most general form. So there was this thing called metropolis Hastings. Or like NH. It's almost exactly like this, but it's like a more general form of this. So for I in 0, 1 over to n, from x I to u from uniform 0, 1 u smaller than alpha xi y xi plus 1 that. We reject. And then here the acceptance function is q y x q x y. Yeah. And so this q is called proposal kernel of this algorithm. And then so this like for example, like this this is like one possibility of this possible proposal kernel. And then this acceptance function, the q term here is kind of like this. It's defined with this. So this is the proposal kernel, and this is how we define the q here. So in the metropolis setting, we realize that the acceptance function does not include this q term. But this is because qxy is equal to qyx in the random walk setting. But in other possible setting, this might not be the case. So we may or may not need to include this term. So well, this is the full picture of the metropolis acceptance function. Any questions so far? Yeah. Let me show you more code. Demonstrate this. Random walk metropolis. There we go. Oh, sure. Sorry. This is the generated output of this 2D random walk metropolis algorithm. Starting point being 10. No, I think that stops. Oh no, that's indeed that's whatever. Good idea. Okay. Yeah, so this is our starting point. And then this mass is kind of like it's ideal because if you know this is like can I run this? Yeah. So like we want to sample from two-dimensional random walk or two-dimensional normal distribution, right? So essentially we have so we should be sampling from this region, right? because this is 0 and 0, right? So we should get values within like these regions. Because if you think about it, this is like one-dimensional picture of like normal 0, 1. Now if you make it 2D, so if you look at it from like the top down view, it'd be like this. And if you go in from the side, it will look something like this. So it's kind of like it goes up and then it forms like a peak near the 0 point, the origin. So which is like this. Now the reason why I start at this like very like aloof point is that I want to demonstrate that this algorithm has the power to to go to this desired region. Relatively fast speed, because you see this one step, 2 step, 3 steps. So in 3 steps, we have already reached this desired region. Pretty neat, right? So if you get this, all these values within this region ideally should follow this normal 0, 1 distribution. So we have already obtained samples from this region. Now, if you change this distribution to something else, and then we just apply the algorithm by rows. I'm not going to explain you the code because it's too long. If you're interested, I can send you a copy. Yeah, so if you change this Harvey distribution and change the code accordingly, we can obtain similar results. Let's stop the share. Some of the things I want to talk about here is that now here this is a sample, right? Also this is a sample. So like when we try to sample from a particular distribution, we are actually already doing some samples. So like the question is, how do you sample from uniform or how do you sample from non-distribution? Well, you can take this as a fact that we could indeed sample from uniform 0, 1 at a relatively good rate, and the same thing. If you know uniform, you can do some sort of transformation and to get normal distribution. Why? Very easy. So if you have x following uniform 0, 1, and then we have a normal distribution. Let's say we say call this F, the CDF. So what's the CDF? Oh, CDF is just probability of x squared y. Greater than y. CDF next smaller than equals to y. And let's see. Yeah. So if y is kind of like a g of x, then we can have g inverse of y dx. This is just the probability of g inverse of y, g inverse of y. And now this is probability of x that's equal to g inverse of y. So, and this is just a CDF of x, and then like x, g, y. But y is some sort of constant of our choice, and then g, assume we know, and assume it's like we can find inverse, then we can just get this relation. So if we can find like a good expression to link x and y, and which we can sample from y, we can always sample from x. We can find an expression that connects x and y. If we can sample from x, we can also sample from y. Because we get the CDF. This is called the inverse CDF. So with uniform, we can sample this sample from uniform relatively well. And then there does exist a G such that it connects X and Y in a good manner, and then the inverse is kind of like easy to compute. Another thing is that we kind of talked about this tuning factor. This tuning factor. So how should we tune it, right? So if you want to tune something, we want to know what's good and what's not good, right? So what's the criteria that we want to adjust or like want to look at when we decide, how well, or should we tune it further or just like stop? So the tuning factor is kind of like, we want to look at this thing called acceptance rate. Acceptance rate. This acceptance rate is just like the proportion. Like, so basically here we say we accept or reject, right? So this is the proportion of the acceptance. So if you do like n trials, this is like the number of accept. In the one-dimensional setting, we want to make this around 44%. And then in the multi-dimensional setting, in high-dimensional setting, with dimension greater or equals to 5, so at least 5. So we will adjust our sigma such that this acceptance rate will be around these values. Then we say it's good. Question: how do we know these values? Do you just pull them out from our head or something? Well, it's actually not the case. We can prove this as well. It's by a series of work by this Gareth Roberts and his collaborators. And essentially, this is like because random walk, right? So multi-dimensional random walk in the long run is just a diffusion process. And we can study the diffusion process. So with the diffusion process, we get this 23%. So we know when dimension tends to infinity, this is diffusion, as we study diffusion, we can get this value. Now this one-dimensional setting is just a random walk, which we can study as well. Now, essentially, this is like for 1D, this is for infinite D. And then we say that for like greater than 5D, we can also use the 23%. Now, this is not technically proven, but it's like we have shown through numerical evidence that this is indeed true. Okay. Any questions so far? Lost 2 people.
No, I think he's going to come back.
Yeah, I think the other guy has some stuff to do.
Yeah.
It's like already won. It's fine, that's fine. Oh, it's time. I'm going to keep the random walk algorithm here, but erase some other stuff because it's going to be useful this time. Okay. Distribution. So in the random walk metropolis setting, we kind of only use the information from the distribution at the acceptance rejection stage. Because here this some random walk is independent of where we are at the state, wherever we are. It's independent of that. We don't care about the time distribution, it's always doing a random walk. So at this point, it's just a uniform distribution, there's nothing involved. And at this stage, we do include information about the target distribution by doing the acceptance rejection. So on the acceptance rejection, this part is kind of like we're sort of like taming our states, taming the samples such that it's like more or less following this distribution. So if you look at this, or this might not be the origin, but like this. So with like the vertical height, like the higher it is, it means that the probability of us taking values from, like, for example, like this point should be higher than, for example, the probability of getting this, right? So we should sample more from like those regions as compared to like the rest, like the tails. So like these are more desirable, less desirable. But that's not really like something we can do through the random walk methodology, because what we're doing here is that assuming we get like a sample here, we just do a random walk, right? Then we may reject this because this value is not good, and we accept this. Then we do another random walk. Just always a random walk, and it does not really include information about the target distribution. So in that sense, it's not very efficient. And how should we better incorporate the information about the target distribution? Well, we need the gradient. Assume we are here. The gradient is going to be like positive, right? So we go this direction. And if you are like somewhere here, the gradient is extremely small, so we just like perturb around this region. But here we'll go here. Go quite fastly. Because the gradient is rather big at this point. So if somehow we can incorporate the information about the gradient of the target distribution, we're actually going to be getting a better sample set. Because the gradient will just help us to move away from those like low probability regions and move faster into the high probability region, just going to stay there, right? Or those high probability of staying there. Now, to incorporate this, we have I'm just going to write the only change here is that and the rest are the same. Obviously, there will be a cube here because it's no longer symmetric, but the rest are the same. So for this MALA, we're just changing this the first step, and then change the alpha column. But that's it. This MALA is the metropolis adjusted. Longevin algorithm. So the step that we use is acceptance. Yes. Fine. Yeah. The step that we do is acceptance rejection is called metropolis adjusted, or like a metropolis adjusting. So it's metropolis adjusted, and the Longevin part comes in from this. If any of you know statistical mechanics or like those kind of stuff, or SDE, stochastic differential equation, you may come across this Longevin equation, which is this like SDE that kind of have this like a depth curve, which is this. And just as I said, it will be very helpful to incorporate information about the target distribution into our whatever this is here. So what we do. Well, not exactly the gradient of pi, but we have gradient of log pi, which, well, just gradient of pi over. So this does incorporate the gradient. Now the question is, why do we do the gradient log instead of just gradient of pi? Any idea?
like someone like because it's normal, someone do like
No.
oh no, sorry, it's general.
Yeah.
It's because in real life we don't really know pi exactly. In real life we don't know pi exactly, but only pi up to a constant term. So like we don't know pi, but sometimes we know c pi some constant pi. So if you do a log, gradient log, what this is still this, right? Because the constant term just cancels itself. This.
Wow, just do the derivation. Oh, c pi. Okay. This is oh c pi. C pi and gradient. One. Just gradient of c pi over gradient. No. Of the c pi. Yeah. Now this c is a constant. So we by doing the log term inside, by putting the log term inside, we can disregard the constant factor. Why do we have a constant factor? Because if you do Bayesian study or Bayesian analysis or Bayesian inference, we will kind of have this idea of a posterior distribution. So we have like some prior distribution, and then we have some new data coming in, and then we just want to update this prior distribution and make it into a posterior distribution. Posterior distribution is always up to a constant term because it's very complicated to compute that constant term system. The new distribution follows the normality condition, i.e. sum up to 1 as an integral. So we always keep this as a constant multiple, some desired distribution, which is why we have log terms from just the gradient. Okay. Finally, we come to our final argument of a Hamiltonian Monte Carlo. Any questions so far? No? Okay. Let me explain what Hamiltonian stuff is. Well, this is like one particular setting of the Hamiltonian dynamic system. So essentially, this is a Hamiltonian of Q and P, where Q is the position and P is the momentum. The Hamiltonian is the sum of this potential at Q plus the kinetic at P. And the idea of a Hamiltonian dynamic is that no matter how these two things change as the system develops, the sum, the Hamiltonian of QP is going to be a constant. So we will try to like accommodate this fact. Now, the Hamiltonian dynamics has this thing called the Hamiltonian equations, which kind of like indicates to us how does this system develops. How does the Q and P changes? Now we have this system of equations. D, I, T. Well, here we assume this is the standard KE, which is the this is like half MV squared. P is MV, right? So like half MV squared is just half of P squared of M. Now this is just like in the multi-dimensional setting instead of like just scalar stuff. We have like vectors and matrices. So kind of writing this weird form, but essentially just a more general version of this half MV squared. And this M is a diagonal matrix, always each of the entry indicate the mass of the particle at the ice entry, the ice entry. Normally we would set them all to be 1 in the Hamiltonian Markov chain setting. No, Monte Carlo setting. But obviously in physics, we don't have to do that.
So these two differential equations tell us how does the position change and how does the momentum change. This is kind of like a continuous kind of updates, in the form of like factor field and such. So like if we have a d-dimensional position with a d-dimensional momentum, the entire Hamiltonian dynamic system will be 2D dimension. So except for the very trivial, not trivial, but like very basic, 1 by 1, so like the 2D. Anything other than that, we can't really plot them in a graph because can't do anything more than 3D, right? The figure. Right. Any questions so far? No? Okay. Now, this system of equations kind of tells us how the Hamiltonian dynamics updates, but it's a continuous kind of update. And we're working with computers, so computers are not continuous, they're discrete. So how do we convert this in, make this into a discrete update? Well, there are a bunch of ways. This most standard and simple way is the Euler's method. I suppose all of you may have heard about the Euler's method, but it's not really good because because it's Euler's. That was like I don't know, like 200 years ago, 300 years ago, something like that. So it was very long time ago. So obviously, mathematics has evolved quite significantly, and we come up with better methods. Is to supersede Euler. So here I want to propose, or not propose, but tell you about this thing called leapfrog. Epsilon. So this is the L is the number of steps. And this is the step size. So for each step, here's what we're going to do. I run out of space. Okay, so this is sort of like the leapfrog for one step at step size epsilon. So what we're trying to do here is that first we update the momentum by half a step by calculating this t plus half epsilon using this formula. Then knowing the half step update of position, of momentum, we update the position using that. And obviously this math we can set it to be 1 in some application, but we don't have to. This is still using the half m square stuff of the DKE. So we have this. After that, we update the second half step for the momentum. So these two are exactly the same, except I've changed like t to t plus half epsilon. Yeah. So these three equations kind of do the 1-2 step of the update of a leapfrog of this Hamiltonian dynamic system. Obviously, we can adjust the size of this epsilon to make changes. And that really depends on how fast or how sort of the accuracy of our numerical argument. Time for more codes. Share screen. Okay. Yeah. Okay, so this is sort of like the graph of one leapfrog updates with some L. I think here I set L to be 25. Yes, L be 25 and epsilon be 0.25. And the starting point. So the current Q being position is minus 1.5 and minus 1.5. And then we are using, so important question. No, important thing. Is that position of the potential here. Now we know that KE is half mv squared, right? What's the potential? Well, potential is just minus log of the distribution. So if you have the minus log of the distribution as a potential, now we do the derivative, it will just be the delta log P, right? It will be the delta, not delta, but the nabla, the gradient log pi, which exactly is what we're trying to do with the MALA. So essentially, this MALA is just like a one-step version of this Hamiltonian log of Monte Carlo, because essentially we are doing this for like L steps, for the L being the number of steps of the leapfrog algorithm. So this sort of like this, this we call it MALA. So MALA is kind of like, HMC is kind of like the more generalized version of this MALA algorithm. Yeah. So okay. Back to what I was saying. So here is this our potential. Still, this is another like a normal distribution, normal 0, 1 distribution case. So that's easy. We get this. So as I said, the starting point is around here, and this shape a bit. So we can see this is the update of position, and then this is the update of the momentum, and then this is the Hamiltonian, the sum of the two, sum of the potential and the KE. And ideally, as we know by property of Hamiltonian dynamics, the Hamiltonian, the HQP should be constant throughout. So it should be on the same line, but obviously this is it will be on the same line, but obviously we are discretizing it, so it doesn't have to be constant, so you kind of perturb it. So as long as the perturbation is kind of like within some sort of range, it's acceptable. So you see that these things are somehow like around this 1.6, 1.5 kind of line. So it's not too bad. And with position point, we can see that it kind of like, we do like small steps along the way, and then eventually we reach somewhere here, which is quite far away from the original point. So it's kind of like a big update, and then like good, because we want this to be like a big update, so we can speed up the time distribution. This is the momentum. Like it's just like illustrate how the momentum changes. So it's not really like important because unless you can do another algorithm, you can just run it again. Let's run it again and get a slightly different graph. See, now we get a slightly different graph here. We go from here and reach somewhere here. Yeah. So by the leapfrog, kind of up. So if we input like a particular position at the starting position, then we do the leapfrog. We get a new position. Then we do the leapfrog again, and we get a different distribution. We do this again. So let's stop the share here. So with this Hamiltonian Monte Carlo, essentially our y will be just leapfrog L epsilon at xi. So here we do a random walk. Here the dynamical updates is using the leapfrog algorithm. The rest are the same. Of course, it's this be the pi q conversion. Yeah. So that's the Hamiltonian Monte Carlo, and that's it. Any questions?
Yeah, but so for the leapfrog,
Yes.
like it doesn't necessarily require, like in this case you only use both functions because they had a relation, but like the leapfrog is it's like its own thing. Like you can work with only one differentiable function.
Yeah, sure.
Yeah, but in this case,
Why
just,
using a
you
leapfrog
just
for
use
the
the,
Hamiltonian dynamic system?
yeah, but I'm just saying, but you didn't like, I mean, you use both of them because obviously, like in this case, like you needed both information, but in general, it's not, you don't need like multiple functions, right? In the,
We'll read about the function.
no, actually, that's never mind, that's fine. So it's,
Basically, the leapfrog is that because if you know the position and the momentum, right? Like we need the momentum to update the position, right? Because we need to know like how the position doesn't change, but if you apply your momentum to it.
wait, so leapfrog is not it's not a general.
It can be more generalized, obviously, but here it's more like specific to the Hamiltonian dynamic.
Yeah, no, so that's what I'm saying. Like, so in this case, like, it
Yeah,
was
so
using
obviously you can try to find. Yeah, no, but the thing about leapfrog is that it involves these two objects, right? We will update the position. Then we'll update the momentum first, then we use the updated momentum to update the position. Then we do the final second half of the update to the momentum.
Okay.
So like in the normal setting, we don't really have like these two objects, right? We don't really have like momentum and position. We somehow just like random walk. We don't need that. We don't need the momentum. It's the same. So we just do like regardless of the position, we just do like always do the random walk perturbation to it. And what this we kind of need a bit, which is why this is like a simple case. You know, when we set Hamiltonian the leapfrog out to 1, we'll get this.
Okay.
Yeah.
Thank you. Yeah.
Another very interesting point, since we can go on this, is that as you can see just now, it takes a while. If you recall the graph or
I think someone said something.
No, sorry, it's fine. It's not a question. Okay. Of course, you start this. Great. Okay, yeah. See, like if you start from here, right, it takes a while for this to go to this like desired region of our distribution. So so if you want to get like the ideal sample, we just cut off. Let's say like we discard like the first 10 samples of these 100 samples, then we focus on the later 90 samples to be those that fall in the particular target distribution of choice. And but how do you decide when to cut off, right? So like how do we know like when is the time that is sort of convergence to the equilibrium distribution? This has to do with concept of mixing time of a Markov chain. Stop it. Stop this. And, okay. So the idea of mixing time. Well, let's say a particular Markov chain with transition relations P and the equilibrium be pi. It's kind of like T being the increment of T such that P D of P T and pi is smaller than some epsilon. D is some epsilon. So if you can find this T star, or you can prove bounds of this T star because it's a random star, we kind of will get a rough idea of how well this particular Markov chain sort of mixes. that's why it's mixing time. So you start off from some like isolated states, and then somehow it mixed together becomes the equilibrium stationary. This is the equilibrium distribution. So we want to study the mixing time of this. So how fast, or like provide a bound for it, like so we know that roughly at what rate, or like whatever stuff that this is happening. Now this metric, we normally use this thing called a total difference metric. Sort of like this. If you have like a two distribution, the matrix will be this. The shaded region will be the matrix. So let's say we have F and G. So D of F and G will sort of be the shaded region. Region A. And then once you control this, you bound this by something like less than some epsilon. So like like the epsilon. It's called epsilon mixing time. Yeah. It's quite interesting stuff to study. So I'm not sure if you guys heard there was this news recently. Not recently, like last year. That this statistician proved some geometrical KLS conduction. So this guy, Chen something, Chen Yuan Si. Yeah. So this guy, when he was, he got his doctorate at Berkeley, and then he went to Zurich for his postdoc. So while he was at Zurich, he kind of proved this conjecture in convex geometry when he was trying to study mixing time. Yeah, because in the mixing time, there's this one approach to how to tackle this mixing time problems by coupling or this bottleneck ratio. I'm not going to go into detail, partly because I have a limit of time, and partly because I don't understand them. But regardless, this guy, he's sort of he tried to solve this statistical problem on to study the mixing time of Markov chain. And he kind of proved this really like a mathematical conjecture, which is pretty neat. It's kind of a big deal. I think now he's going to Duke or something. Let's see.
It's so sudden.
Yeah, yeah, he's not at Duke. It's now AP at Duke. Yeah, pretty good stuff. Yeah. Quite interesting.
Oh, Duke. Oh, okay.
Duke, yeah. Yeah, so yeah.
North Carolina?
Yeah, North Carolina. Yeah. Right. Yeah, I think this should be it for my talk, and thank you all for coming. Yeah, that's it.